Okay, so while our projector is thinking about it, we'll get started for today. So we went over chapter 1, which is introduction to terms in thermodynamics, equation of state, quick review of vocabularies we'll be using, and also calculus, right? So that's chapter 1. And then previous lectures, we went over chapter 2, which is first law of thermodynamics. We went over definition of concepts, including heat, work, and energy, right? So our final conclusion coming from the first law of thermodynamics is that there exists a state function, a thermodynamic state function, total energy E, that's conserved for the process taking place in a closed system. Later on, we'll replace that total energy with internal energy, assuming the system is at rest, no external field. And from the internal energy U, we define the term enthalpy, which is H equals to U plus PV. So that's of chapter 2. The most important take-home message from chapter 2, talking about the state function, is knowing what's the difference between a state function and line integral. Right? So state function like internal energy and enthalpy, these are the terms that, well, if the initial and final state are the same, they are the same value. But there are also two different terms called work and heat. So these two are processes dependent functions or line integrals. Okay, bye. And heat and work, both of them are dependent on the path that we take to get from A to B. So different paths, you might have different work and heat. And today we're ready to move on to chapter 3. And in chapter 3, we'll introduce second law of thermodynamics. And from there, we'll start to define a new state function, entropy. So we won't get to entropy today, but today we'll talk about the second law of thermodynamics and the idea of heat engines. And then next lecture, we'll use the concept of heat engine to define entropy. And later on, after definition of entropy, we'll went over calculation of terms of entropy and also physical meaning of entropy, like what exactly is entropy. So that's the preview of chapter 3. And as you probably know, next Wednesday, we'll have our first midterm exams. Lots of you are already sending me messages. So here is a general answer. I will send out an announcement on Bringler this Friday. So in that announcement, that will include what are the coverage of your midterm 1 exam. And also like what's the format of the exam gonna be, where and when the exam gonna take place. And next Monday, we'll have a buffer lecture, basically going over a review of everything we discussed, and also with like problem sets, 2 example problems together. So that's the general plan for midterm exam. All right, so another quick administrative announcement is I won't be here tomorrow, so I'll have to move my office hour to Thursday. So the same place in my office. So if you want to stop by, office hour will be Thursday this week. Okay, any other questions on administrative things? All right, perfect, let's get started. So first thing first, we will start by reading the second law of thermodynamics. There are 3 different ways to say it. We'll read it together, and then we'll see what you think about them. First one is called the Kelvin-Planck statement of the second law of thermodynamics. Basically reads, it is impossible for a system to undergo a cyclic process whose sole effects are the flow of heat into the system from a heat reservoir and the performance of an equivalent amount of work by the system on the surroundings. Or the other way to put it is we're saying a cyclic machine cannot completely convert the random molecular energy of heat flow into ordered motion of mechanical work. You cannot 100% convert heat into work. Another way to say it is that it is impossible for a system to undergo a cyclic process whose sole effects are the flow of heat into the system from a cold reservoir and the flow of an equal amount of heat out from the system into a hot reservoir. I don't know what you're feeling about these words. When I first read them, that's me. I'm like, okay, I recognize every word in this statement, but what exactly does it mean? So today, we'll start from these seemingly abstract concepts, and in chapter 3, we'll go over them step by step. So hopefully at the end of chapter 3, when we come back and read this statement again, they will make much more sense to you. All right, so let's get started on chapter 3. First of all, one of the things that keeps showing up in our definitions here are the cyclic processes or heat engines. So let's just give heat engine a good and nice definition so we can use heat engine as a tool to understand our second law of thermodynamics. So getting started, when we say heat engine, effectively we're just saying this is a machinery. What exactly is that machinery is out of discussion from this lecture. So a heat engine will convert some format of random molecular energy of heat flow. So when we say heat flow, what we're saying is these are random molecular energy. These are energy, yes, but they are randomized molecular energy. While work, on the other hand, are ordered, right? So when we're doing work, like if I'm throwing my adapter to the sky and like in the process, I'm doing work, right? So this process of work is a macroscopic energy, but it's directionary. It's like to a certain direction, it's ordered instead of heat transfer that's not ordered. So with these terms in hand, we can start by thinking about a system. So this is one cycle of a particular specific heat engine. We can imagine on the top, we have a hot reservoir at a higher temperature. So this one is basically temperature at like higher temperature. That's subscription H, meaning it's at higher temperature, like a hot tank of water. And on the bottom, we have a cold reservoir at a lower temperature, Tc. Now, in the process of transferring heat, we can imagine the hot reservoir transfer heat into a heat engine. And in this process, we have a QH. Right, so that's amount of heat or absorption heat by the heat engine from a hot reservoir. Or the other way to put it, your system, which is a heat engine, is absorbing heat from the hot reservoir with a positive QH. In the meantime, you can also imagine the heat engine is given the rest of the heat it absorbed. Some of them was transferred to work, and some of them was passed down to the cold reservoir. So we have a QC, which is the emission of heat from the heat engine to a cold reservoir. All right, but in the process, the difference between your QH and QC becomes work output by the heat engine. And then we have work. So that's the work done by the heat engine to the surrounding. So that's why work itself is a negative number. Your heat engine is absorbing heat, so QH is positive. It's emitting the rest of the heat to the cold reservoir, so QC should be a negative, and then outputting work to the surrounding. So W is also negative. So this defines like one cycle of a typical heat engine. So in this process, we can define the term efficiency, saying like how efficient my heat engine is transferring heat into work. So in that, we can define my efficiency of this heat engine to be E equals to the work output per cycle over energy input per cycle. Or in this case, the work output is this negative W, and the heat input is QH. Right. And since my work output is a negative number, we can also generalize it into the absolute value of work over QH. And what else do we know about efficiency? So we can use our first law of thermodynamics to give this efficiency a little bit more insights. Using our first law of thermodynamics, what do we know? We have the total energy, considering this entire cycle being close to the rest of the universe. We have delta U equals to Q plus W. So the total amount of heat plus the total amount of work must add up to be 0 for this entire thing, including hot reservoir, heat engine, and also your cold reservoir. So that's our first law. And in here, if we're moving the terms around, moving my work to the right-hand side, and my Q equals to QH plus QC, right? So your total heat equals to the amount of heat transfer from the hot reservoir to the heat engine, plus the heat transfer between your heat engine to the cold reservoir. So this equation effectively becomes negative W equals to QH plus QC. All right. And in here, we have defined our efficiency to be work divided by QH. So what we can do is divide both ends by QH. And we end up getting negative W divided by QH equals to 1 plus QC over QH. And the reason we know we want to divide both ends by QH is because we're trying to get efficiency. And by reading the definition of the efficiency, we see that QH is on the bottom. So that's why, yes. Oh, this one is coming from the first law of thermodynamics. So the total delta U coming from the cyclic process must add up to be 0, right? So my total heat equals to QH plus QC. And the Q plus W equals to 0 for delta U. And from here, we can add one more step. So translating my W minus W over QH to my efficiency. And we effectively get to my efficiency equals to 1 plus QC over QH. All right, so far only defining a heat engine and just putting the terms and using our first law of thermodynamics. So this gives us another way to say, like, what does first law of thermodynamics tells us? My QC and QH must have different signs. One of them is heat transfer to the heat engine. The other is heat engine transfer heat to the cold reservoir. So it must have different sign, whether it's a heat engine or a heat pump. It doesn't matter which direction you run the machine. So that tells me my efficiency will always be a number smaller than 1. Also fits our expectation using our first law of thermodynamics, you have conservation of energy. So far, so good. So this part, it's, again, some kind of reformulation of our first law of thermodynamics, and also introduce the concept of the heat engine. Now we have one cycle of the heat engine. Next step is we want to take one more step. Now we have a way to define the efficiency of the heat engine. Now, from the human perspective, we want this heat engine to be as efficient as possible. So naturally, scientists come to the next point of thinking about, okay, what is the most efficient heat engine we can build? So that comes to our next question, which is how can we find what is the maximum amount of work you can output from a heat engine? We'll first give you the conclusion, and then we'll use our second law of thermodynamics to prove that this principle holds true by setting up a special cyclic machine. So the statement is called the Carnot's principle. It states the maximum amount of work from a given supply of heat is obtained with a reversible engine. So when we say reversibility, remember it's always like going at a very slow rate. You can reverse the direction of that engine at any given time. So a reversible engine. So Carnot principle states a reversible engine is the most efficient one. And how should we prove it's true or not? So scientists come up to say like, okay, can we build a hypothetical engine to prove that the cardinal principle is true, which says the most efficient engine is a reversible engine. So here's the thing. Here's the example cycle that we built. Imagine we have two different heat engines on the left and on the right. One of them is a heat engine, so it takes heat from the hot reservoir, passes heat to the cold reservoir, output work. The other one is a heat pump, so basically means you're running it the reverse order. From the cold reservoir, your heat engine is accepting work from the outside and heat up to transfer the heat back into the hot reservoir. So it's the reverse of the heat engine. So in this case, if we look at the left one, assuming we have a reversible heat engine acting as a heat pump, so transferring heat, so the surrounding does work on the reversible heat pump and then pump energy from the cold reservoir to the hot reservoir. So in this process, we'll have a negative QH reversible and a positive QC reversible. Right, so we're taking heat from the cold reservoir, doing work on the heat pump, and then pumping heat out to the hot reservoir. So that's why this value is positive, this value is negative, and my work reversible is a positive number. It's accepting, the surrounding is doing work on my heat pump. And for my left cycle, we have my irreversible. And in here, since my left-hand side, my heat pump is a reversible heat pump, meaning like it doesn't matter in which direction we're running it. So the absolute value of your QH reversible must equal to the absolute value of your QC reversible. Or we can write my Q reversible equals to my W absolute value over QH reversible. So far, so good. So that's my left cycle. And let me just put QH reversible equals to negative QC reversible for this reversible cycle. And hypothetically, let's assume the kernel principle is incorrect, and there exists a super engine. So when we say it is incorrect, we're just saying, okay, so what if there exists a super engine that's more efficient than my reversible engine? So we're manually set my super engine's efficiency, E super, is larger than E reversible. And then in this process, we can write out my QH reversible and then my negative QC reversible. And my super engine is not a reversible engine, so my QH is, the absolute value of QH is larger than your QC. And it outputs energy. 1 second. Yes?
If it's not reversible, why do we have this like QH reversible, QC reversible for the super engine?
That one, okay, let me double check. Okay, I think I'm making a mistake. We shouldn't say they're equal, but in this case, we can still define my irreversible equals to W over QH reversible. So when we're defining the efficiency, we're always using the QH, we're always using the higher reservoir energy differences between your heat engine or heat pump to the hot reservoir. But yeah, I did make a mistake. They shouldn't be equal. Thank you for putting that out. Okay, so in this process, what we end up getting is you have a QH, wait. Sorry, this one should be super.
Yeah, that's what I meant.
Okay.
Know what's going on with the other one.
The other one is also wrong. Thank you for pointing out. But in this case, we're manually set my QH reversible on the left-hand side equals to my QH super. So this one we can alternate, right? Just make sure you run that, you run both cycle at a certain rate so that the heat input is the same as heat output. So that's something we can manipulate. Okay, so this part is the setup of my two different engines. So in this case, if we want to know what's the relative amount of the work that's being transferred in these cases, we have our definition of my E equals to negative W over QH, or W equal over QH, absolute value of W over QH. But since we're manually set my negative QH reversible equals to the absolute value of QH super, they have the different sign, but the magnitude, we can set them to be equal. So we can say that because my efficiency of my super engine is larger than efficiency of my reversible engine, we get W super larger than W reversible. Or the only thing that comes out from this cyclic process with the hypothetical super engine is some kind of network output. All right, so in this hypothetical engine, if there exists a super engine that is more efficient than the reversible engine, the only effect coming out from this hypothetical hypothetical cyclic process is output of heat, output of work from heat transfer. So this violates our second law of thermodynamics. If we go back to the original statement of those confusing sentences, or saying a cyclic machine cannot completely convert the random molecular energy of heat flow into ordered motion of mechanical work. And that's the same as the Carnot principle, saying a reversible engine is a most efficient engine. All right, so this part, we're using the second law of thermodynamics to prove that a reversible engine is the most efficient engine. How are we feeling so far? Yes?
I'm sorry, this is right. You said that it's violating it because the hypothetical is saying that the work output is supposed to be equal to the...
So the reason this hypothetical system is violating the second law of thermodynamics is if we look at what's coming out from this cycle, right? If we let this cycle run, effectively we're just like circulating heat in a heat pump and a heat engine. But somehow we magically got net work output from this cyclic process. And this positive net work output violates the second law of thermodynamics. Yes.
Wait, I'm so sorry. How did we establish that the super engine is more efficient?
Well, that's the whole point, right? So we're trying to disprove the Carnot principle. So in order to disprove it, we must say, okay, so this is not true. If it is not true, there must exist an engine that's more efficient than a reversible engine. And that's why we say, let's assume there is a super engine. And then we find out, okay, if there exists a super engine, we'll violate the second law of thermodynamics. So we're using the second law of thermodynamics to prove the Carnot principle. Yes?
Why are you allowed to just set QH reversible is equal to negative QH super?
Well, so in this case, you can imagine you have a heat pump and a heat engine. So these two doesn't need to run all at the same time. Like, let's say this one is more efficient than this one, right? But you can run them, like one of them, like run one cycle on the left-hand side. The other one, you can run it at like 0.8 cycle. So that's something you can manually set. You can only set one of them to be equal to each other. So in this case, we're setting the top one to be equal. So basically, you're controlling the amount of heat flow into the hot reservoir and the amount of heat going out from the hot reservoir to be equal to each other.
Oh, and the reason why you can do that and get different results is because one of them is more efficient than the other, right?
Well, the other way to put it is we can set these two to be the same. It doesn't matter which one is efficient or not. It's just something you can do experimentally. Like imagine you're keeping the internal energy of your hot reservoir unchanged throughout the whole process. right? So that's how you maintain your QH reversible have the same magnitude as QH super. Yes.
So are you saying that during this experimental setup, so the system is actually not isolated, means that it will have outside interaction?
No, we're saying like this entire system, like everything, including hot reservoir, cold reservoir, heat engine, super engine, and some kind of filling. So everything drawing on this picture is isolated from the rest of the universe. So we're talking about this, what's going on with this everything taking consideration together.
Does the heat engine also release work to the surroundings?
Sorry, I can't hear you.
Does the heat engine also give off work to the surroundings?
Right, so this is the thing. This is the network output we're saying.
That's from like the super engine. Does the like heat pump also release work?
Well, so as a heat pump, it accepts heat from the surrounding so that it can pump energy from the cold reservoir to the hot reservoir.
Okay, but it itself doesn't do work on it.
Yeah, itself doesn't do work. It absorbs, or the surrounding does work on itself. All right. So far, for this one, the most important take-home message is that a reversible engine is a most efficient heat engine because of the second law of thermodynamics. All right, so we get to the conclusion of a reversible engine being the most efficient one because of the second law of thermodynamics. And from here, we'll continue to use the idea of a reversible engine being the most efficient engine. And now let's think about, from the thermodynamic point of view, what's the most efficient, like cyclic process we can build so we're transferring heat to work? That's of real interest, right? Because we always want to convert heat to work, to do work, to do things that we want in a mechanical engine. So now let's considering a cycle called Carnot cycle with ideal gases. So I'll start from specific cases of a Carnot cycle with ideal gases only. Next lecture, we'll generalize our conclusion into like anything that we want. So in this process, we'll do the setup together. So what we will do is go over the 4 steps in the cyclic process one by one and do what we did last lecture, which is for each process, identify what is heat, what is Q, what is W, is it positive or negative, and how does your delta U change along the way. All right, so let's do it together. I'm gonna draw a PV diagram on the board, and then we'll just go over it one by one. And let's say we start from here. Reading it, the first step is called an isothermal expansion at TH, or a higher temperature. So we start from here. Right, so it's an isothermal expansion. Now, expansion telling us my final volume is larger than my initial volume. My temperature remains the same. So for my ideal gas law, we have PV equals to nRT. My temperature is the same, and it's not changing. R is a constant. Volume increase, my pressure must decrease. So where's my point 2? Must be somewhere here. Now, in my lecture note, I connected these lines with straight line, but in reality, they shouldn't be straight line. I just don't know how to draw it more accurately. And by the way, our class picture on Bruyler, that's a Carnot cycle. Okay. So we're drawing from here, right? So from 1 to 2. And for this process, my temperature is not changing. For ideal gases, my delta U must equal to 0. And my W is negative. Because my system, my gas is expanding, it's doing work on the surrounding. So my Q1 must be positive. So far, so good?
Are we doing delta H?
Oh, delta H is also 0. So we'll just stick to delta U for now. Okay, next up. Now we have the gas expanded at QH. We're ready to cool it down. But the process of cooling it down, we're gonna have an adiabatic cooling of my gas. All right, so we start from TH, and we're cooling it to some kind of lower temperature. Again, my temperature is decreasing, so the product of my pressure and volume must also decrease. So in this process, we end up here at a lower temperature TC. And in the process of my 2 to 3, this one is adiabatic. So we know my Q equals to 0, right? By just knowing it's adiabatic. And what about U? My delta U, 2 to 3, is this positive, negative, or 0? My temperature is decreasing, so my delta U must be negative. And consequently, using our first law of thermodynamics, we have work from 2 to 3 also must be negative. And also that's why we end up with a volume that's larger than the volume of 2. So far, so good. And then, well, once we're at my T3, my cold temperature, we're ready to undergo an isothermal compression. So now we're decreasing the volume, maintaining the temperature at Tc. So now thinking about the process. Again, it's an isothermal compression. So my delta U from 3 to 4 must be 0 because it's isothermal. It's compression, so my work must be a positive or a negative. It's compression.
Positive.
Yeah, so it must be positive. And my Q, 3 to 4, must be a negative. All right. And we're compressing it back to here. That's our process 4. And at the end, we have our final reversible adiabatic heat up to my TH. So this process, my Q, 4 to 1 equals to 0 because it's adiabatic. And my work, 4 to 1, must be positive. And my delta U, 4 to 1, must also be positive. All right, so this part, we're just using something you already know, which is heat engine, and also calculating or predicting WQ and delta U, how do they change with respect to these isothermal or adiabatic processes. And the whole point, remember, for the Carnot cycle, as we scientists, we want to build a cycle that is efficient as possible. So back to our original goal. Now we have this Carnot cycle. Now for Carnot cycle, by definition, it is a reversible cycle, meaning like if you run it 1, 2, 3, 4, or 4, 3, 2, 1, or 2, 3, 4, 1, however you like to run it, it will always have the same efficiency. It doesn't matter in which direction you run it. Now setting it up with the Carnot cycle, we're ready to calculate the efficiency of the Carnot cycle, right? We want to know what exactly is the efficiency of this Carnot cycle and how can we make it more efficient. So, but in the process, we find out something quite interesting. I'm just going to put out some of the things we know. So first of all, we know that the irreversible or efficiency of a reversible cycle of any reversible engine working between different temperatures is the same. Like, again, that's what I say. If you run it like forward or backward, it will always have the same efficiency. And then we can assume now my efficiency must be a function of my temperature hot reservoir and the temperature of cold reservoir. So the goal here is, can we express the efficiency of my Carnot cycle using TH and TC? All right, so that's a goal. And you can imagine doing that for other kind of reversible cycle. I'm just using a Carnot cycle as an example here. Now, what are the things we know? We have our first law of thermodynamics, du equals to dq plus dw. We know that in this process, we only have reversible PV work, because Carnot cycle itself, by definition, is reversible. We have dw reversible equals to negative PdV. And then we're dealing with perfect gas. So we have PV equals to nRT, and then du equals to CV dt. So these are the things we already know. And now let's think about what is happening in this case. I'm just going to use this part. So we start from the first law of thermodynamics. And the reason we're starting from the first law is, well, we know that delta U will end up to be 0. So the first law seems like to be a good starting point to give us a way to simplify our cycle here. So our first law tells me du equals to dq plus dw, and plug in some of the things we already know. Like for ideal gases, my du equals to Cv dt equals to dq minus PdV. So nRT over V dV. All right, so that's my du equals to dq plus dw. But in here, we want to move the terms a little bit so that we can solve this integral, because eventually we want to do the integration of du equals to delta U equals to 0 for this whole cyclic process, because I mean, my internal energy is a cyclic function. So in this case, I want to divide both ends by temperature so that my last term doesn't have temperature in it. So that becomes Cv over T dt equals to dq over T minus nR over V dV. So far, so good. And then, well, we know that my internal energy is a state function. So if we're taking the cyclic integral of all 4 steps, and the way we represent cyclic integral, this integral with a circle, basically saying we're integration over the entire cyclic process. And we can write my Cv over T dt equals to my cyclic integral of dq over T minus nR over V dV. And now we're making an interesting observation. Now bear with me a little bit. Thinking about it, this term here, we only have some function of T, which is my heat capacity V, and like my isochaloric heat capacity. And we know for ideal gases, my isochaloric heat capacity is only a function of temperature, and also like over temperature with respect to change of temperature. So this term becomes an ordinary definite integral, meaning we only have one variable in this integral, which is temperature. And we're taking it a cyclic integral, meaning we start from TH, we end up getting TH. So if we're doing the cyclic integral for this term, we must end up to be 0, because my initial temperature and final temperature is the same. Right, because we only have one variable, and that variable has same initial and final temperature. So it doesn't matter what's the expression here, this cyclic integral must vanish to be 0. So far, so good? The same applies to this last term here. We have the cyclic integral of nR over V as like dV. So the only variable on the last term, assuming the system is closed, my number of moles is not changing, the only variable here is volume. And you have same initial and final volume. So this term must end up to be 0 as well. So by looking at the Carnot cycle, we make an interesting observation that this term here, which is the cyclic integral of the Q over T, this term must add like integral to 0 for the cyclic process. Or the other way to put it is we find out this dq over T term for Carnot cycle is behaving like a state function. Right, so remember, what is a state function? A state function is assuming we have the same initial and final thermodynamic state. The state function have the same value. Or in this case, we find out the cyclic integral of the dq over t must vanish to be 0. And in our next lecture, we'll generalize this conclusion and give entropy a good definition. But in here, I just want to see, like, we're just setting up the Carnot cycle using our first law of thermodynamics, and in the process, we're also assuming the reversible cycle being the most efficient one, also uses our second law of thermodynamics. We end up making the observation that dq over t must be some kind of state function. Yes?
For the first part, why did we divide by t again?
This one, I want to make sure this one doesn't have any temperature dependence on the last term. That's all. I'm just trying to move the temperature with t.
Okay.
Yeah.
Can you say again why dq over t is a state acts as a state function?
Okay, so what is a state function? Right, so a state function, meaning as long as you have the same initial and final thermodynamic state, the change of that state function equals to 0. In this process, well, we're taking the cyclic integral of 1, 2, 3, 4 of the cyclic process. We say that dq over t will vanish. So that's why we're making the assumption that dq over t must somehow is related to a state function. Yes?
Can you explain why the other two are 0?
Okay, so the other two are 0 for the same reason. In both cases, these two are ordinary integrals with only one variable in them. All right, so on the left-hand side, the Cv over t is only a function of temperature. You can imagine that to be any kind of functional, but as long as your temperature is the same, initial and final state, this integral must vanish for the cyclic process. Because your T final equals to T initial. Same applies to volume. So far, so good? Okay, so now we make this observation, but remember what we're trying to do at the beginning. We're trying to express my efficiency of my Carnot cycle as a function of TH and TC. So let's do it. So from there, we come up to this point where my cyclic integral of dq over t equals to 0 for my Carnot cycle. And it's a cyclic integral, so we can rewrite this one to be my integral between 1 to 2 dq over t plus 2 to 3 dq over t plus 3 to 4 dq over t plus 4 to 1 dq over t equals to 0. This is just writing out the 4 steps of my Carnot cycle. Some of the things we already know by working out the Carnot cycle, right? Like for adiabatic processes 2 to 3 and 4 to 1, my Q must equal to 0. So my 2 to 3, this term is 0. 4 to 1, this term is 0. Because they're adiabatic processes. That's by definition 0. So we further simplified it to be the isothermal process 1 to 2 dq. So for 1 to 2, my temperature is constant to be TH plus my 3 to 4, which is here, my temperature is constant, which is TC, and that adds up to be 0. All right. Or, since this one is always at the same temperature high, and this is the temperature cold, so or QC, we can take my constant temperature out from the integral, becomes 1 over TH, 1 to 2 dQH, plus 1 over TC, 3 to 4 dQC equals to 0. And this just comes out to be my QH over TH plus QC over TC equals to 0. So far, so good? And then from here, I'm just going to use this space here. Now I want to move my Q with Q, temperature with temperature, because after all, we want to get a efficiency as a function of temperature. So what we end up getting is this QC over QH equals to negative TC over TH. So this is just moving the terms. And at the beginning of our class, we went over to derive my efficiency equals to 1 plus QC over QH. And we got efficiency equals to 1 minus TC over TH. And this is true for Carnot cycle, ideal gas. So far so good. So we started by introducing the concept of heat engine. And we start talking about the Carnot cycle because we want to build a cycle that's as efficient as possible. So we manually set our Carnot cycle to be a reversible cycle so that according to the second law of thermodynamics, this is the most efficient cycle we can get. And then we went over the derivation of the cycle and come up with an expression of efficiency equals to 1 minus TC over TH. Or the other way to put it, the larger the difference between your TC over TH, and note that these are Kelvin temperature, it's not Celsius temperature. So the larger the difference between your TC and TH, the smaller this value becomes and the more efficient your Carnot cycle is. And in the process, we also identified this interesting observation where the cyclic integral of your dq over t must vanish to be 0, hinting there exists another state function coming from the Carnot cycle. So in our next lecture, we'll start from here and give the dq over t term a more settled definition. But before we do that, let's think about what do we get from this calculated efficiency. If we're taking the engineer way of thinking, that is, how can we make our heat engine more efficient? Or let's assume we have some kind of coldest reservoir in hand to be 10 degrees Celsius, and we want a heat engine that's at least 90% efficient. What's the minimum temperature required for that hot reservoir? Right. So how do we approach this kind of question? The first thing we want is we want it to be as efficient as possible. So we want a reversible engine or cycle so that we have the maximum efficiency. And that's why we know we can assume we have a Carnot cycle. Ideal gases. All right, so the first step is to know which equation to use. And because we want an engine as efficient as possible, we want a fully reversible engine or fully reversible cycle. And then thinking about my E maximum, that's 90%. Or we have my irreversible E Carnot equals to 1 minus TC over TH. And the maximum, minimum efficiency we want is 90% or 0.9 equals to 1 minus, my TC is 283 Kelvin over TH. You plug in the calculator, you get my TH equals to 2,830 Kelvin. I'm running out of time, but there's another example question that you can try, which is given you have a kernel cycle heat engine that tells you how much work that's being done at what efficiency, and find out like W, QH, and QC for one cycle. And the result is in our annotated note. And I'll see you on Wednesday.